Hello everyone, welcome to the lecture 2 of Strength of Materials, and this particular lecture is specifically for GATE Aerospace, right? So in the previous lecture we revised some concepts. Okay, we solved some concepts, we solved some questions, PYQs based on the GATE Aerospace that has been asked all these years, and today we are going with the new concept, that is Mohr circle. Okay, so I have seen that from the Mohr circle in the GATE Aerospace, they are not asking very complex questions. They are asking very easy and very simple questions. So as far that they have asked, and in the end, we will also solve some questions based on the Mohr circle, right? So let us first see Mohr circle. So it is nothing but just a circle. So you have some axis. Okay, so you guys have already seen that in the mathematics that you have this y-axis, this is your x-axis, and you are drawing some circle over it. Okay, or you are like placing some circle over it. This is your center, 0 comma 0, whatever it is. Okay, so this is a circle. Okay, right? So this is how the circle works, actually also in the Mohr circle as well. Now then, uh, let let us see that if I have a beam. Okay, so this is a beam. Okay, and wait, sorry, before we go with the Mohr circle, let us fix our sign convention. Okay, so our sign convention. Okay, so this is our sign convention, that is the sign that we are going to follow. Okay, so let us see that what we are going to follow. So if it is in the clockwise direction, so let's say that if it is in this direction, okay, um, then that will be positive. Okay, and if it is in the anti-clockwise direction, then that will be negative. Okay, this is clockwise direction. Now what is in the clockwise direction and anti-clockwise direction? So let's say that this is my shear stress distribution over it, for this particular beam, and let's say this is top, and this is my shear stress distribution over this particular beam. Let's say this is also top. Okay, so you can see this is going to rotate in this direction, right? So anti-clockwise direction, this is going to rotate in this direction, that is clockwise direction. So we are considering it positive and this is negative. Earlier in the previous session, I have also told you the sign convention. Okay, and that was our like normal sign convention. So how was it? So it was like that. Okay, and this we are considering the positive, and this we are considering the negative. Okay, sorry. Um, so this we are considering the positive, right? This is the positive sign convention. Okay, so this is positive, and if I want the negative one, so it will be something like this. So this will be negative sign convention, right? So this was the earlier sign convention that we are following, right? Now then, let's come back to the Mohr circle. Okay, and for the normal stress in the Mohr circle, how we are going to see the same as the normal. So this will be my plus, and this will be the minus, negative sign convention and positive. So this is same, let's say. Okay, now come back to again, let's come back to the Mohr circle. So let's say that this is my sigma and this is my sigma. Okay, this is my beam and I have sigma. So this is sigma xx, and you know what is this? This is the phase and this is the direction. Okay, right? So I do not need to tell this. Okay, so you guys must have revised that, right? So this is sigma x, okay, in the xy direction, and this is how we are going to follow. Now then, in the Mohr circle, so this Mohr circle is the graphical representation of the state of stress. So what is Mohr circle? So it is graphical representation of the state of stress, right? So this is what is Mohr circle. Mohr circle is the graphical representation of the state of stress. Now then, we have seen that in whenever we draw something normally in mathematics, okay. So what we have, this is x-axis and this is y-axis, okay. But here we are trying to draw the Mohr circle, okay. And what is a Mohr circle? Mohr circle is the state of stress. Mohr circle is the graphical representation of state of stress, okay. So stress, we have two types of stress, that is sigma and another is tau. This is the normal stress, this is the shear stress, right? You guys already know that. So which axis should represent the normal stress and which axis should represent the shear stress? So x-axis will represent the normal stress and y-axis will represent the shear stress, okay. So this will be my normal stress and this will be my shear stress, right? So this is how we represent the normal stress and shear stress, right? Now then, I have a beam. Okay, so the question was earlier that I have a beam. Okay, and I have only single state of stress, that is sigma. And how we are going to represent this state of stress over this particular axis. Okay, so you know we follow already this x and y axis. Okay, so this axis we follow and this is the z axis, right? Okay, this is the z axis, right? And this is the origin. So we already follow that. Now then, how can we represent the stress? So first thing first, understand that when we are going to represent this in the form of circle, then we are representing it in the 2D format. Okay, so state of stress can be 3D over the 3D beam. So let's say that I have a beam like that, and so I have a stress sigma 3, this is sigma 2, and this is sigma 1. Okay, so I can have a state of stress or system like that where I will have sigma 3, where I will have sigma 1, and I will have sigma 2 as well. But currently we are following the 2D system, right? And in the 2D system, we have this sigma 1, okay, this sigma, okay. So now how we are going to represent it, okay. So, you know, what we will do, we will represent the sigma on x-axis and tau on y-axis, okay, and this will be our origin, right? Now what we are going to do, we are going to represent these values, okay. So what we will do, we will represent this particular. So how can we represent, where we will represent it, okay. So we understood that we have to represent sigma on x-axis, right? We have understood that sigma is going to be represented on x-axis, but how? Okay, so which part should we take? There are two faces, okay. So this is phase 1, the x phase, and this is phase 2, y phase, okay. So which phase we will represent where and how? So you know, we will represent this by a, okay, this phase as a and this phase as b, okay. So we will represent sigma 1. So let's say that this is my, this is, and this particular x-axis represents the entire length of the sigma or the normal stress. So let's say that this particular length is my sigma, okay. So I will represent it by a, and on the x, on the this phase, like a phase, let's say that on this phase what we have, we have sigma. Do we have any shear stress? No shear stress. So that is where sigma comma 0. So a will be represented by sigma comma 0 because there is no shear stress, no tau here, okay. On b what we have, 0 0, okay, no shear stress, no normal stress. So this will be 0 0, no shear, no normal, okay, right? So for your convention, I will write this like this, okay. So sigma comma tau. So this is how we are, x is with sigma and y is with tau, okay. So this is how we are going to represent. So on x-axis, on x direction, what we have normal stress, but we do not have any shear stress. Here we do not have any normal, we do not have any shear. So that is why 0 comma 0. So this will be my b, okay. And if you remember or not, I don't know, but I have already told you that in earlier classes that radius, how will we find out the radius? So radius will be under root of sigma x minus sigma y by 2 whole square plus tau xy whole square. And what is this? This is again, what is this? This is again the tau max. This is again the tau max. And there is one again another formula for tau max, that is sigma 1 minus sigma 2 by 2, mod of sigma 1 minus sigma 2 by 2. And this particular thing represents the radius, this entire thing. So this is again radius. Okay, this is again radius, or you can call it this is tau max. Okay, don't get confused. This is same thing. Okay, now then, so this is our, we have located the sigma, we have located the point on the x-axis. Okay, now what we have to do is that we have to find out the center. So what we will do, we will bisect this. So we will bisect this and we will find out the center. So what is the center? So center will be sigma x plus sigma y by 2 comma 0, because we are going to bisect this entire line. Okay, so that will be our center. So what is our center? Center is sigma x. So what is sigma x? So this is your sigma x and this is our sigma y. So sigma x is sigma and sigma y is 0. So what will be our center? Sigma plus 0 by 2 comma 0, right? So what will be our center? Center will be sigma by 2 comma 0. So something here. So this particular point will be sigma by 2 comma 0, right? Now I want to draw the circle. So by taking this particular point as a center, this line as a radius, I will draw a circle. So how I can draw the circle? So this will be my circle. So this is my Mohr circle. Okay, so this particular circle is my Mohr circle. Okay, and this point, okay, so this should be the maximum point. I have drawn it wrongly. So okay, so actually I am not good in drawing, but yes. So this particular point is called sigma and star, okay, and comma tau max, in plane tau max. So this tau max is in plane tau max, okay. So this is in plane maximum shear stress, okay. Do not forget this one, okay. And this is sigma and star. And what is sigma and star? Sigma and star is nothing but the center. So that is your sigma x plus sigma y by 2. This is your sigma and star. Okay, we have already seen that in previous session, right? Now then, so there are some important points about the Mohr circle. So the very first point is that, so let's say that I would say some important points about Mohr circle. Some important points about Mohr's circle. Okay, so what are those important points? So we will see one by one. So the point one is every radial line is a plane. Okay, every radial line is a plane. Now what does that mean? So let's say that this is my Mohr circle, this is my sigma, and this is my tau. Okay, sorry. So this is my tau. This is my Mohr circle. Let's say this is my Mohr circle. So, and this is the center for the Mohr circle. So this is a radius, 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 this is a, so each radius is a plane in itself. So each radius is a plane in itself. Okay. So every radial line is a plane. And principal axis, second thing is that principal axis is represented by, sorry, not principal axis, principal planes are represented by, so principal planes are represented by radial lines, what radial line represent a plane and principal plane. So we are talking about the principal plane, that is why there is a radial line. Okay, so principal planes are represented by radial lines lying on which axis? Can you guess? Can you guess? Take a pause, take a minute pause, and can you guess that what would be which which uh, which type of radial line? So this is my sigma, and this is my top. So this is represented by, let's say, y, and this is x-axis. Okay, and let's say that this is my Mohr circle, for example. Okay, and this is my center. So I have several radial lines here. So I have this radial line, I have this radial line, I have this radial line. Okay, and I have this radial line as well. Okay, so can you guess which radial line will represent the Mohr circle? This is 0. Okay, for principal plane, which radial line will represent for the principal plane? So to represent the principal plane, which radial line should we consider? Okay, can you guess? So this will be on x-axis. Why on x-axis? So you have already seen that the location of principal plane. Okay, so location of principal plane. So how do we find the location of principal plane? You do tau theta is equals to 0. So you make the shear stress 0, and this particular, so where will be shear stress 0 in this particular figure, in this particular graph? That is on the x-axis only, right? So here shear stress is 0, but we have some value for the normal stress. So that is why principal planes are represented by radial lines lying on x-axis. This is very simple. Anyone can guess. So you just have to use your so you just keep your brain open and focused. Okay, so you can see that. So that is why tau s theta 0. So tau s theta is 0. So where is tau s theta 0? So that is your shear stress 0. Where is your shear stress 0? So your shear stress will be 0 on the x-axis. Okay, so y value will be 0, right? Now then, there is another thing, that every plane represented by Mohr circle, represented by Mohr circle by double of its actual angle, double of its actual angle, sorry, by double of its actual angle. Now then, this third line. Okay, so let us explain this one as well. So I will explain here only. I will explain here only. So let's say that this is my Mohr circle. Okay, so let's say that I have this particular beam, and this is sigma, and this is sigma. Okay, and for this particular beam, I have made the Mohr circle. Okay, so how would that look like? Let me redraw it. Okay, so I have to erase this one. You guys have already understood this part, right? So so it will be touching the origin point, right? And this is my top, and this is my sigma, and let's say this is my center, right? So this is the maximum. So this is the sigma n star, comma, tau max. Okay, so this is the maximum shear stress. This is the radius, right? So radius is the tau max. Okay, and this is the let's say that this is A, and this is my B phase. So this is my A is sigma comma 0, and this is my B is 0 comma 0, right? A is sigma comma 0, right? So that is my A, and this is my B, right? And this is my center. Now the, so you can see from here that this maximum shear stress is represented by 90°, but in actually theta, maximum shear stress theta S1 is represented by 45°, right? So this is half of this angle, right? This is half of this angle. And not only that, you can see, you can see, you can see the principal plane. So this is again one reference plane, this is again one another reference plane, right? So this will be like that. So let's say that this is sigma, and this is my another reference plane. Okay, so this angle is 45 degree. For the shear stress, there will be some tau and there will be some sigma and theta. Okay, so you guys already know that. Okay, and if I see another plane, okay, so this particular plane is another principal plane, and that particular principal plane is represented by 90 degree. Okay, so and you can see here it is representing 180 degree. So this particular thing BC, I am talking about the BC. Okay, so this particular plane or the plane is represented by 180 degree, but it is half of the angle, so it is represented by 90 degree, right? You can see from here to here or here to here, you can see present it like that. Now then, if that is clear, then let's see some another point. Wait. So the fourth point is that center of the Mohr circle. So center is represented by sigma x plus sigma y by 2 comma 0. Okay, and fifth point is the radius. The radius of the Mohr circle is equals to tau max, and this is equals to sigma 1 minus sigma 2 by 2 mod of sigma 1 minus sigma 2 by 2, or you can use this formula sigma x minus sigma y by 2 whole square plus tau xy whole square. In some book, what they do is that they take this 2 outside and then they bring 4 here. Okay, so that is just the algebraic manipulation. Okay, and you guys can do this. Okay, so don't worry about that, so don't get confused about this. So if you see something, just try to understand it. Okay, just try to write it with a pen paper and solve that, and you will definitely understand it. Okay, so we have seen how to draw the Mohr circle. Okay, let's take some more example. Okay, so for example, I have some another beam. Okay, some another beam. Okay, and in this particular beam I have some shear stress. Okay, so I will erase this one, sorry. So this particular beam, I have this particular shear stress. Okay, so let us solve some another example. So for example, I have one another beam. This beam I have, and I have some shear stress tau, and there is no normal stress. Okay, so now then, what you are seeing here, you are seeing here this particular face A. So what how do we represent this? So there is no normal stress. Okay, right? You guys already know that. How do we represent x comma y, right? So sigma comma tau. Okay, so there is no shear stress, so that is 0. No normal stress, that is 0. But we have one shear stress, so we will put tau. Okay, on B face again we have 0 comma tau, that is B. Okay, so now then, this is not tau. Okay, so this is not so we have seen the sign convention earlier. Okay, right, we have seen the sign convention that if it is clockwise, that is if it is in this direction, clockwise direction, then it is positive. Okay, so if it is clockwise, then we call it positive. If it is anti-clockwise, then we call it negative. Negative sign convention. Okay, so so if it is like that, that is positive. So you can see the upper face. Okay, so you can see if this is the beam that we have, this same beam. Okay, so that is why, so B will be positive 0 comma tau. Okay, and this one is anti-clockwise direction. Okay, right, this one is anti-clockwise direction, so this face. Okay, so you can see, if I draw some another replica of this particular figure, right? So this is like that. Okay, and this is again moving in anti-clockwise direction. So this particular A phase will have 0 comma minus tau. So this is minus tau, right? Don't get confused now why I have put here minus tau. That is why earlier I have put here plus tau, and then I showed you that how can we change the sign. Okay, so that is minus tau. Now we have got the point A and point B. Now I am going to draw the coordinate system, and then there I will draw the Mohr circle. So this is my coordinate. So sigma, and this is my tau. Okay, this is my x-axis and this is my y-axis. Okay. Now then, I'm going to represent the point A. So point A is 0 comma minus tau. So this is 0, x-axis 0, y minus tau. So this is minus tau. Okay, and similarly y 0 tau. So this is tau, this is tau, this is C. Okay, so this will be so this will be point B, this will be point A, and this particular entire length, so we will bisect it. So it will come here and we will draw a circle. So this will be our circle. Okay, and this is 0 comma 0, right? This is also our center. Okay, now so center is represented by sigma x plus sigma y by 2 comma 0. So sigma x is 0, sigma y is 0. So that is why center will be 0 comma 0, right? That is why center is 0 comma 0 at 0 comma 0. Now then, radius is under root of sigma x plus sigma x minus sigma y by 2, right? So not plus sigma x minus sigma y by 2 whole square plus tau x by whole square. Okay, so sigma x sigma y is 0. So what will be that? 0 plus tau x square. So we have tau whole square. So that will be tau. So this is your radius. Radius is tau. And of course, even by looking at the picture, you can say that this is my shear stress. Okay, this is my radius. Sorry, not shear stress. So this is how you are going to represent a shear stress. Okay, and what is this particular condition is called? This condition where there is only shear stress, no normal stress, that is called pure shear, right? And earlier we have seen, okay, so earlier we have seen this particular Mohr circle. Okay, this is touching the y-axis. Okay, and we have seen that there is only one type of normal stress. Okay, so this is called the case of pure bending. Okay, this is called the case of pure bending. Let us see for the case for pure bending. Okay, so what is the meaning of pure bending? Okay, so when we will study the bending stress chapter, okay, bending stress chapter, bending stress. So when we will study the bending stress chapter, then there we will mm, understand about it in more detail. Okay, so don't worry about it now. Okay, so there is one condition in the bending stress, that is sigma by y is equals to m by I is equals to E by R. This sigma is the normal stress. Okay, and this m is the bending moment. Okay, so whenever I say pure bending, this means that this particular sigma, so let's see this particular relation, sigma by y is equals to m by I. So this implies sigma is equals to m y by I. Okay, so this sigma is the normal stress, m is the bending moment, y is the distance from the neutral axis, and I is the moment of inertia. Okay, or you can say that, yes. Now then, let us see that. So sorry. So now let us see this particular sigma. This sigma is the stress. Okay, this sigma is the stress. Okay, and this m is the bending moment. Okay, this m is the bending moment. And now if you see the relation, then sigma is directly proportional to m. Okay, so which means that this sigma is going to affect this bending in the beam. Okay, so let's say that I have a beam here. Okay, and I have a stress here, and this stress is the sigma. Okay, this stress is the sigma, or this stress is the uniaxial. Okay, so uniaxial, what does that mean? Uniaxial means there is the stress on this particular beam in only one direction. Okay, it can be like this, or this can be like this. Okay, so this is again the uniaxial state of stress. Okay, or again this is the uniaxial stress. Okay, so this particular sigma is uniaxial. Okay, and that is why it is unique. Okay, that is why it is called unique. Okay, and this m is the bending moment. And if I say this is the pure bending, this means that this bending moment is either constant or this bending moment is uniform. Anything can be possible. So if this bending moment is uniform, then we will call it pure bending. If this bending moment is constant, then again we will call it pure bending. Okay, and there is one another thing, that is this stress should be unique or uniaxial. Okay, so this particular thing should be unique. Okay, so that is the case for the pure bending. Okay, and we have seen the Mohr circle for this one. So the Mohr circle will look like something like this, and the Mohr circle for this one will look like this. Okay, so this is the Mohr circle, how the Mohr circle will look like for the pure bending state of stress. Okay, now then let us see the state of stress for a 3D system, like Mohr circle for a 3D system. So let's say that I have a 3D body. Okay, so I have a body. Okay, I have a beam here. Okay, and this beam is we have a 3D beam. Okay, so we have some sigma 3, we have some sigma 2, and let's say this is my sigma 1. Okay, so in case of thin cylinder, so this is particularly the case of thin cylinder. Okay, so do not worry about that. Okay, so if we study about the thin cylinder in the chapter for thin cylinder, okay, we will study about this in more detail. Okay, so let's say that sigma 3 is 0, and this sigma 2 is sigma, okay, sigma by 2, and this is sigma. Okay, so in thin cylinder we have a state of stress. Okay, and that state of stress are divided into two parts. So one is called the hoop stress. Okay, the another one is called longitudinal stress. Okay, so this hoop stress is represented by sigma h, and longitudinal stress is represented by sigma l. Okay, and this hoop stress is also considered as sigma 1, and this is also considered as sigma 2, but it is not a rule. So you can call it sigma 2, you can call it sigma 1, whatever you want you can call it. Okay, so don't worry about this. If we study the thin cylinder, then there we will see in more detail about the hoop stress, how the hoop stress is developed, what is the condition behind it, how the longitudinal stress is developed, and what is the condition behind it. Okay, so we are going to see all those things in detail in the vocation. For now, understand that. So let's say that if I take a 2D system, and if I represent this, and I will represent it by sigma l, and this is my sigma by 2, and I will represent it by sigma h, and this is my sigma. Okay, and I will also call it sigma 1, and I will also call it sigma 2. Now you can see I have three state of stress. Okay, so I have sigma 1, that is sigma 1 is equals to sigma. I have sigma 2, sigma 2 is equals to sigma by 2, and I have sigma 3, that is 0. I have considered it as the state of stress in third direction or z direction is very minimum, or it is 0 compared to these two. Okay, so now I have three state of stress, and I want to represent it into the Mohr circle. Okay, Mohr circle, and Mohr circle is a 2D representation of a system. Okay, so it is a 2D system. Okay, so how can we represent this? So we will represent this in a pair. So let's say that I have a circle C1, so I will represent it as sigma 1 and sigma 2. Okay, then I have circle C2, and I will represent it as sigma 2 and sigma 3, and I have circle C3, and I will represent it as sigma 1 and sigma 3. Right, now let us represent all those circles. Okay, so let's say I have taken our axis system, sigma and top. Okay, and now I will represent the circle C1. Okay, So C1 with sigma 1 and sigma 2. So what is our sigma 1? Our sigma 1 is sigma. Let's say that this is our sigma. And what is our sigma 2? Sigma by 2. Let's say this is the sigma by 2, half of the length. Okay. So this is sigma by 2 and this is our sigma. Okay. So this will represent as our, this will represent as B and this will represent as A. So let's say that this is A and this is B. And what is A? Sigma by 2 comma 0. And what is B? Sigma comma 0. Right? So this is sigma comma 0, sigma by 2 comma 0. This is my origin. This is my origin. Sorry. Uh, okay. Just give me a second. Just give me a second. Yes. This one as well. Right. So this one is particularly my origin. Okay. So let's say that this one is my origin. Okay. And this is point A. This is point B. Okay. And for now I will erase it so that it looks neat and clean. Okay. You understand that point A here, from point A, and here is point B. Okay. And now if I want to draw the circle over it. Okay. So how can I draw? I will take this one as center. This is center C1 and I will draw a circle like this. Okay. And this is my circle. Okay. So now then, if I see I want to represent my C2, I will show more things in this. But first draw the circle C2. Circle C2 is sigma 2 comma sigma 3. So sigma 2 is sigma by 2. So this point is my sigma by 2 and sigma 3. This point is my 0. That is sigma 3. Okay. So again, if I draw this, okay, I will represent it by another color. Okay. So let's say I take the red one. So if I draw this, so this is my center C2. Okay. And this 2 will be the same height. This 2 will be of same height. Okay. So I don't want to, yes. Right. So this 2 will be of same height. Okay. And this is tau max. Okay. 1 and 2. Okay, this is tau max, same. So I will say tau max 2 is equals to tau max 1 is equals to tau max 2. Okay. Now then let us represent the third one. So third one, how can we see? So how can we draw the third one? So sigma 1 comma sigma 3. What is sigma 1? Sigma 1 is sigma. So this is the sigma. Okay. This particular is the sigma. This particular length is sigma. This particular length is sigma 1, let's say, and this particular length is sigma 2, let's say. This particular length is sigma 2. This is touching, not overlapping like this. Okay. So I'm not drawing it to scale, so that is why it looks like that. Okay. So let's erase this too. Okay. So if I draw this, then okay, I don't want to. So this will be my circle. Okay. And this will be the center. Just a second, guys. Just a second. I'm making some mistake there. And this is again touching here, not crossing it. Okay. So this is again touching here. Okay. Okay. So this should be touching. Yes, very good. No, this is again wrong. Wait. So like this. And this is my point B, sigma comma 0. This is my point A, that is sigma by 2 comma 0. And let's say I am drawing the third circle. Yes. So this is my center C3. Okay. And this is again my Tomax. Right. So this is again my Tomax. So you guys can see here, and by seeing the picture, you can see this is Tomax 3. Okay. So which one has the maximum value of Tomax 3? So if I say Tomax absolute, then what will be that? The maximum of Tomax 1, Tomax 2, Tomax 3. So what will be that? Tomax absolute, what will be? Tomax 3. And what is the value? So we will calculate the value right now. Okay. So how can we calculate the value? So how can we calculate Tomax? The Tomax is nothing but mod of sigma 1 minus sigma 2 by 2. Okay. So that is Tomax 1. Tomax 2. What is mod of sigma 2 minus sigma 3 by 2? And what is Tomax 3? That is mod of sigma 1 minus sigma 3 by 2. Okay, so we are taking the pair from here, so you can see for the reference. Okay, so what will be that value? So tau max 1, what will be that? Sigma 1 is sigma and sigma 2 is sigma by 2. Okay, so sigma 1 minus sigma, so that would be sigma by 4, and this will be equal to tau max 2. So this value, this particular value will be equal to sigma by 4. Okay, and what is tau max 3? So tau max 3 will be sigma by 2. This particular value will be sigma by 2. So this value will be sigma by 2. Okay, so what will be the absolute tau max? This will be sigma by 2, and this is also the radius. Don't forget, we have discussed that in the previous one. Okay, so we have discussed here, right? Radius. So this is the radius. Okay, so radius also has mod of sigma 1 minus sigma 2 by 2. Okay, so this is how the radius is again. And how can we calculate the center? So you already know the center. How can you calculate? Sigma x plus sigma y by 2 comma 0. So this is how you will calculate the center. So you can again calculate the center, sigma x plus sigma y by 2 comma 0. So this is how it is. Okay, and every radial line represents a plane. So this is the reference line. So we take the reference line on x-axis generally. So let's say that this is the reference plane. Okay, and from here I will measure those. Okay, I will measure those. Okay, and from here I will measure this one as well. So this one as well. Okay, so this is how I will get all this value. So this is the state of a stress in 3D system. So this is how we can represent the state of a stress if I have a body and I have a 3D state system. 3D stress system, not a state system. Sorry. Okay. Now then, the tau max absolute. So maximum of tau max 1, tau max 2, tau max 3, and tau max absolute will be sigma by 2. So how do we calculate it? Mod of sigma 1 minus sigma 3 by 2. And sigma 1 is sigma and sigma 3 is 0 by 2 mod, and that will be mod of sigma by 2, and that will be sigma by 2. Okay, so that is the absolute tau max. Okay, now let us talk about the previous year questions that have been asked in the Mohr circle. So well, in GATE Aerospace, they have not asked much complex questions in the Mohr circle. They have asked some simple questions. So they told you the condition for pure bending, right? What is the condition for pure bending? And they have given some circles. So like this, then they have given like this, then they have given like this. Okay, and then again they have given like this. Okay, so they are asking that option A, option B, option C, and option D, out of this which is the condition for pure bending? So which is true? So you have seen now that for pure bending this condition is true and this condition is true, this is false and this is false. Okay, not only that, they have also asked that which possible Mohr circle, which is the possible Mohr circle. Okay, so they have asked something like that. So they have given you like same circle like this. Okay, so they have given like this, option A, then option B they have given like this, Then option C, they have given like this. And then in option D, they have given like this. And they are saying which is the possible Mohr circle, like which can be the possible value of the Mohr circle. So which is the possible like Mohr circle? Okay. So which of the following is true? They are asking. So this is true. Mohr circle can be like this whenever it is a pure shear. We have seen that case of pure shear. Okay, this is the case of pure bending. This is the case of pure bending. This is not possible. Okay, so this is wrong. Okay, so they have asked like this. So what I will do is that in the next like session, I will try to bring some questions about the Mohr circle. I will go and look into the PYQs. I will also try to bring the Mohr circle questions from the mechanical engineering. Okay, and that has been asked in the gate. Okay, and then we will see. I will also try to find out some questions from the books. So guys, don't forget to read Gere. Okay, so Gere and Goodno. So you go and read Gere and Goodno, see the Mohr circle chapter and study about that. See some theoretical questions, because gate always surprises you. So they may ask some theoretical questions from the between. Okay, so you have understood the concept. Now go and see some theories about it. Okay, solve some questions, and then definitely you will be able to understand this particular concept. Okay, that is all for today. Thank you. And in the next lecture we are going to see some more about the normal stress and shear stresses. Okay, and then after that we will move on to the bending. Okay, so we will see the isotropic and isotropic, okay, homogeneous material. No, not only that, we will also see about some like volumetric strain and all. Okay, so how does the strain behave in that particular manner and all. So we will see about that strain behaviors as well.